In this video, we're going to look at a concept called hybrid atomic orbitals. The reason why we're going to discuss hybrid atomic orbitals is because in the formation of a covalent bond in previous videos, we've looked at the overlapping of atomic orbitals. However, there are some more detail that is needed to explain how some covalent bonds and the orientation that these bonds are created in molecules are done that overlapping of atomic orbitals can't fully explain. So let's look at an example. Let's look at the molecule H2O, and let's look at how oxygen and the two hydrogens will overlap their atomic orbitals. So looking at the orbital diagram for oxygen with 6 electrons, that has 2 electrons in the 1s subshell, 2 electrons in the 2s subshell, and then 2 unpaired electrons in 2 of the 2p subshells. The valence electrons in oxygen are going to be the electrons that are the 2 paired electrons in the 2s, and then 2 unpaired electrons, 1 in each of the p subshells. Now, how this would traditionally work is, for the bonding pairs to occur, is that 1 electron in each of the 2p subshells that have electrons in them will overlap with the subshell, the 1s subshell, in each of the hydrogens with their 1 electron. And so what this would traditionally look like would be you have 2p subshells. So say this first one here is the one in purple, and then the second 2p subshell is this one in green. I'm just not showing the third 2p subshell. But what would happen is the 1 electron in the 1s subshell for the first hydrogen and the 1 electron in the 1s subshell for the second hydrogen would overlap with the respective p subshells. And so, for instance, it would do something like this. So we come over here and overlap here, and this one would come over and overlap here. And essentially, you would be having now your overlap for each of the orbitals that now creates this bond that we kind of draw as a line. Now, if we did that and this was true, the angle between these two now new bonding pairs would be 90 degrees. We know that that is not true. And in fact, when we draw the structure of oxygen with 2 hydrogens, our water molecule, the angle that is formed with the overlap of the 1s and the 1s from the hydrogen and the 2p orbitals from the oxygen actually give us an angle of 109.5. For theoretical, in experimental situations, it ends up being something closer to 104. And so why is that? Why is that we're getting a much greater angle than what would happen with a traditional overlap? And it turns out that there's something that happens to the orbitals in the center atom to equilibrate all of the various orbitals that are utilized in this process to create an equal distribution of energy. And what we do is we call this thing called hybrid atomic orbitals. So it looks something kind of like this. The hybridization of orbitals happens in this particular way. You have to combine wave functions by this mathematical process called linear combination of atomic orbitals, or LCAO. And the number of atomic orbitals which gets hybridized depends on the number of areas of high electron density on that atom. And so this is really important. So there are obviously 5 different ways that atomic orbitals can hybridize because we know of 5 different spatial orientations associated with the VSEPR theory of high areas of high electron density. And that's 2, 3, 4, 5, and 6. These are the possible numbers of areas of high electron density. So let's look at what happens with each one of these. So if we look at if you have 2 areas of high electron density, the type of hybridization that occurs in that center atom is called sp hybridization. Why is it called sp? Because it uses one s orbital and one possible p orbital. It combines these orbitals and it creates 2 new hybrid orbitals. These hybrid orbitals have a name, and they're called sp and sp, and they're shown together on one axis here. What does this look like via energy? So if we look down here at this graph down here, you can see that if you happen to have, say, the orbitals in the beryllium atom, and it happens to have, say, 2 electrons in the 2s orbital and none in the 2p, okay? You're going to want to hybridize 2 orbitals, an s and a p, in order to create the molecule BeCl2. That's how many areas of high electron density would be on the beryllium atom. And so what will happen is we'll use one of the p orbitals and the s orbital, right? The p orbital and the s orbital. We will hybridize them, create 2 new orbitals that now have different energy levels. So if you'll notice that this energy level goes up and this p also goes down. But see, this p right here, here still exists. This 2p here still exists. They're unhybridized. But now you've created 2 new orbitals in place of the original 2p and the original 2s that are called sp. And there will be an electron in each one of those. So this is what we call sp hybridization. This allows for an even energy level distribution and overlapping of the orbitals that this molecule will create so that the angle can be the best possible repulsion angle given according to the VSEPR theory. So what about 3 areas of high electron density? If we're going to use 3 areas of high electron density, then we need 3 orbitals. We always start again with an s, and this time we'll use 2 p orbitals. We will hybridize all 3 of these, combine them together, and essentially we will create 3 new hybrid orbitals, and those hybrid orbitals will have a new name. Their new name will be sp², sp², and sp², and they're all shown together on the same graph combined here that I just circled. It will give you an arrangement of trigonal planar, which according to the VSEPR theory is the shape that we should see of the electronic geometry if you have 3 areas of high electron density. What does that look like energy-wise? Again, you have a 2s and 3 orbitals in the 2p. You're going to use 2 p orbitals and a single s orbital, combine them together to create 3 new sp² orbitals that have a combined, like an average energy value, where your unhybridized 2p orbital stays exactly where it was beforehand. What about 4 areas of high electron density? 4 areas of high electron density create something that we call an sp³ hybridization. Why is it sp³? Because you use one s and all 3 p orbitals. You're going to go through this hybridization. You're going to create, from using the 4 orbitals, 1s and 3 p's, 4 new hybrid orbitals. Those brand new hybrid orbitals have the name of sp³, 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 and sp³. And they're spaced around the XYZ axis in the orientation of tetrahedral that you can see all combined together in this diagram. What does that look like energy-wise? You use all three of your p orbitals, one of your s orbitals, and now you create a hybrid set of sp³ orbitals. And remember, your s and your original p's no longer are there because now you just have all sp³ orbitals. This also occurs for 5 areas of high electron density. Hybridization now includes, because we've used all s and all p orbitals that would be considered valence, hold valence electrons. We're going to have to add an additional orbital, and we're going to use 1d orbital out of the possible 5 orbitals. And what the orientation that this gives, it's going to use those all 5 of those orbitals, combine them together and create 5 brand new hybrid orbitals. And those hybrid orbitals will have the name, each one of them, of sp³d. And they will be spaced in orientation around the XYZ axis that you see here. Each one of these, all 5 of these, are hybrid orbitals called sp³ds. That then gives you the shape of trigonal bipyramidal, according to the VSEPR theory. The same of that would be true for 6 areas of high electron density. We're going to add an additional d orbital, so now you're going to have 6 total new hybrid orbitals. And these hybrid orbitals will all be called sp³d² orbitals. You will have 6 of them that will be spaced in the orientation that you see here that gives you the orientation of octahedral, the same as you would see in the VSEPR theory as well. So what's kind of our take-home message from this particular video? The take-home message is that based on the number of areas of high electron density, there is a particular hybridization that occurs with the atomic orbitals on that center atom to create the orientation that we see according to the VSEPR theory. And so the thing that I would remember most are the possible numbers of areas of high electron density and their respective hybridization associations. So if you have 2 areas of high electron density around the center atom, it will hybridize 2 sp orbitals and create 2 sp orbitals. If it's 3, it'll be sp2. If it's 4 areas of high electron density, it's sp3. 5 areas of high electron density, sp3d. And 6 areas of high electron density is sp3d². So this particular number association and hybridization association is what I would like for you to know at the end of this particular video.